Today we're going to talk about OpenCL kernel programming, and in particular we're going to look at the data types and device memory. Here is a table of the scalar data types we can use in kernel functions. As you can see that there are a lot of familiar data types: Boolean, character, unsigned, short, long integers, etc. These data types are very similar to the data types in other high-level languages like C or C++. There are some data types that are specific to OpenCL programming. For example, these three types are related to pointers, and this one, int ptr, this is a signed integer to which a void pointer can be converted. Similarly, unsigned integer pointer is an unsigned integer to which a void pointer can be converted to. This pointer difference is a signed integer produced by pointer subtraction. As you can see that these three types are useful when we operate on memory addresses. Size t is a signed integer produced by a size operator. You can figure out the size of a data type, for example, integer or float. And lastly, the void is untyped data. Now you may wonder that where is the double type? Double type is available in high-level languages. It turns out that in OpenCL framework, double is a pretty special data type. Double is supported only if the target device supports the CL Kronos floating point 64. CL Kronos FP64 is an extension, and that extension is to indicate whether a OpenCL programming framework supports double type. Not all the OpenCL devices support double type. We can find out this extension whether an OpenCL framework supports floating point using CL get device info. If this extension is supported, that means this OpenCL framework from this particular vendor supports double type. And in our kernel program, we can use this pragma OpenCL extension CL KHR floating point 64 : enable. If you want to enable every supported extension, you can replace this CL underscore KHR underscore FP64 with all. So all the extensions that are supported by this particular OpenCL platform will be enabled. Let's look at this short example. In this example, we'll try to enable the double type extension by using this pragma. Now we use ifdef so that we can choose to enable or not to enable. And in this kernel function, double test, we take three arguments. They are all global memory object, A, B, and out. And if we do have data type, what we're going to do is we will perform the multiplication on double data types, and also we're going to store the result into this output of memory object. We have this typecast here because, as we define in this kernel function, the output argument is a floating point. If we do not choose to have the double type, then we just use this regular floating point multiplication. We can use float and double if double is enabled, and half data type in OpenCL kernel functions. Float by default is a 32-bit floating point number. It supports the IEEE 754 format that includes this infinite number and not available, and it will be round to nearest even number. For double data type, this is not required to be supported on every OpenCL device. And for the cases that the double type is supported, then we can perform multiply and AND operation, and we require that this multiply and operation be supported as a single operation. We can also use half data type. That means it's a floating point number, but it's only 16-bit wide. Byte order. OpenCL standard does not mandate the byte order. Byte order simply refers to Endianness. Endianness is a way that a computer architecture defines how the multi-byte variables are going to be stored in memory. We have option of little endian and big endian. Let's look at this example. We have an unsigned integer x, which is a 32-bit integer. If we write its hexadecimal value, it's going to be 01, 02, 03, 04. Now we can store this binary number in memory, and depends on the endianness of the device, the byte orders of this particular integer will be different. If we have a little endian device, and then this is how we're going to store this integer. Assuming these are 4 bytes and these addresses indicates the orders of these bytes in the physical memory. And you can see that on the little endian device, we actually have the least significant byte stored in the lowest address. So the second least significant byte, this 03, will be stored at the next address, and so on. And the most significant byte of this integer, this 01, will be stored at the highest address. In contrast, big endian devices will store these bytes in a different order, in the opposite order. And specifically, we will store the most significant byte of that number at the lowest address. This is FF00. And then the second to the most significant byte will be stored at the next address, at address FF01. And finally, the least significant byte will be stored at the highest address. You can find out the endianness of an OpenCL device using CL get device info. Vector data type. We've seen vector data type in the past in many of our examples. Vector is actually arrays that contain multiple elements of the same type. These vectors have the fixed length, and you can declare the length. Operators can apply on every element at the same time, and that's one of the benefits of using vector data type instead of using arrays. It's much simpler and faster than using arrays. Let's say you have these 3 arrays, A, B, and C. Each of them is a 4-byte floating point array. And we're going to perform this element-wise addition on A and B and put the result into C. If you have these arrays declared as float A bracket 4 like this, then you have to have a for loop where you have a loop iteration I, and this I goes from 0 to 3. And you can perform this addition on every element of these 2 arrays and put the sum into the 3rd array. To perform the same thing, you can use vectors. In this example, we declare A, B, and C vectors of floating point with 4 elements. That's why we have here float 4, and that's to indicate that we have a vector, and the elements in these vectors are floating point, and each vector is a 4-element vector. And then we can use A plus B and assign this sum to C. This single statement, this single line of code, will apply this summation operation, add on every single element of A and B we're doing element-wise addition and put the sum into C. Similar to the floating point vector we just showed earlier, there could be different vector types. The vectors could contain 8-bit signed numbers or unsigned numbers, or a short, this is 16-bit signed, or a 16-bit unsigned. So these are very similar to the scalar types, although we can have this number at the end to indicate how big is the vector, how many elements are in this vector. For these double data type and half data type, these are two special data types that may or may not be supported by an OpenCL device. As a result, you may or may not have a vector of double data type or half data type. Although you can have an arbitrary number for the vector size, but typically we consider to use n so that the large vectors can be put into memory, follow the memory alignments, and also these vectors can be operated efficiently. For example, for older MacBooks, you cannot operate directly on floating point 16 because you're talking about, in that case, 16 times 32, then that's a 512-bit vector. And depends on the processors, you may or may not be able to operate on such long bit vectors using a single instruction. You can query the size of these vectors by using CL device preferred vendor with type, and that will give you information how many elements in a vector you can successfully process within one single instruction, or using one simple line of code. For example, you can say get device info and put the device as the first argument. Then I want to query the device preferred vector with character. Then that will give you the vector size for character type of vectors, and that in that case it's 16. And you can change this to a short, and that will tell you what is the preferred vector width for a short type of vectors. Now, because we can find that the devices may prefer different vector width, what we can do is to use this get device info and use the information that we obtain from this preferred width and use it to set options for CL build program. For example, based on the vector size, we can say that we will define a floating point vector of 4 if the preferred size is 128. Otherwise, we'll define a floating point 8. That means we have a vector of 8 floating point numbers if the vector size is 256. To initialize a vector, we can use a very simple statement like this. So we declare data_vec as a floating point vector of size 4. Then we can put the initial values in this, within this pair of parentheses, so that we know we're going to initialize these values 1.0 to the first element, and 1.0 to the second element, 1.0 to the third element, and 1.0 to the fourth element. Of course, depends on your actual purpose, you can change these values to the initial values that you want to put into these vectors. In this case, the components actually have the same value, so you can use an even simpler statement like floating point 4 parenthesis 1.0. You don't have to put only scalar values into these vectors. You can actually initialize a vector using smaller vectors. For example, if we have two vectors of size 2, A and B, and both of them are initialized in this way, using the scalar values. And for this vector C of size 4, you can actually initialize this vector using this first two smaller vectors A and B. Finally, you can also create a vector with a combination of scalars and smaller vectors. For example, here, if you have RGB, this vector of 3 elements initialized in this way, then you can initialize RGBA, which is a vector of 4 elements, and using RGB, this smaller vector, and together with a scalar value 1.0. There are different ways to select elements or components in the vector. You can use number indexing. You can also use letter indexing, which we'll show later. And also you can use high, low, even, odd to indicate a subset of the indices or subset of the elements. Let's look at this example. We have a vector of 16 characters, and this vector is called MSG. Here's how we initialize this vector. We declare the vector type, and also we put in the values into these 16 elements. As you can see that these are letters, so we'll just use single quotation mark to indicate this is a character. And overall, we have 16 characters or 16 letters that we'll put into this 16 element vector of character type. And then here are some examples of how we refer to the elements in this vector. In the first line here, we are doing msg.s0. MSG is the vector name. Dot and s, this is to say that I want to find element with certain index. And this s0 is to say that I want to find out the element with index 0 in this MSG vector. And this is how we initialize it. So as you can see here, that index 0 is actually letter H. So we're going to get this element and assign this element to this another variable A, which is again a character type. So as a result, we will set this new variable A to this letter capitalized H. Similarly, we can find S4. So we're going to find out the letters with index 4. So we start from 0, 0, 1, 2, 3, 4. So this 0 is the one element that we want to assign to variable B. Similarly, we can find the 8th element and so on. Now the last one, SC. C here is to indicate that we want to find the element which is at index C, and C is hexadecimal. So that is 12, and this is going to be 12, 13, 14, 15. So this is the M that we will retrieve, and we will assign that value to another variable D. We can access multiple elements using similar methods. In this example, we're using the same message vector that has been initialized. Then we can find out all the first 8 elements from this vector by using this msg.s 0, 1, 2, 3, 4, 5, 6, 7. And in this way, we're going to be retrieving all the first 8 elements from this message vector and assign those elements to this variable E, which is declared at an 8 element vector of character size. So that is to set E to this hello pro, the first 8 letters. Likewise, we can choose other elements, and we can in fact to reverse the orders of these elements. And here we're trying to say that we want to retrieve the 5th element, then the 4th element, then the 3rd element, then the 1st element. So we're actually picking letters from this vector and assign this letters to a new vector F. So in particular, we're trying to figure out this capitalized P, and then O, and then SL, and then this E. This next example is similar, although here we're trying to get all the element in the reverse order. So we're using here msg.s fedcba 9876543210. So we're going to get all the element out, but in the reverse order. The next statement here is to get some element out of the message vector, and you can see that we're using different sequence, different orders, and then we'll use this smaller vectors as a way to initialize a longer vector G. If we want to change the element in these vectors, we can use similar method to find out the values or locations of these elements. And this first line here is to get the fifth element from this vector and reassign that value to capital O. And this next line is to get 4 elements. We pinpoint this index B, 9, 8, and 6. Then we're going to assign new values to these 4 elements using this one single line. The other examples are very similar, and you can just look at those and try to understand what they're doing. In some situations, we may use letters as the indexing method instead of using the indices, numerical indices. For example, here we have a coordinate, which is a vector of 4 and with type floating point. And we can initialize this vector using this float 4 and 3.0, 5.0, 7.0, 9.0. So we know that this is a 4-element floating point vector. And at index 0, the value is 3.0. At index 1, the value is 5.0. At index 2, the value is 7.0. And at index 3, the value is 9.0. You can, of course, use 0, 1, 2, 3 to index these elements. But I want to show you here that we can use these letters, in particular X, Y, Z, W, as indices to find out these elements. And this is particularly useful for vectors with 4 elements. So we assign these letters X, Y, Z, and W as a way to represent a 4-dimensional space. And then you can use X, Y, Z, W, these letters as indices to find out these elements. For example, here we can choose coordinate.x. That will find out the first element of this 4-element vector. And so this 3.0 will be retrieved and copied to this this variable A. Beyond that, you can use a combination of these letter indices like we do in the previous example where we use numerical indices. So here, coordinate.xy, that is to say that we want to use the first and the second element from this 4-element vector and assign those 2 elements to this new vector E. Similarly, we can modify the corresponding element in the vector using the letters indices. And so like in this example, we assign 2.0 to the first element of this 4-element vector coordinate. We can also use high, low, even, odd to select a subset of the components in a vector. Dot high refers to the components in the upper half. For the vector size of odd numbers, use the number of elements divided by 2, and that's the upper bound of the element that we're going to be using. This is going to be from n divided by 2, n divided by 2 plus 1, n divided by 2 plus 2, and so on until n minus 1. If it is dot low, and we're going to be using the lower half of this vector. So the indices for these components will be from 0, 1, up to n divided 2 minus 1. Dot even and dot odd are easier to understand, because dot even is really referred to the even indices, and dot odd refer to the odd indices. So let's look at this example. We have a vector of 8 unsigned short, and this vector name is shorts, and we assigned these initial values to this vector. So we have here the initial values are 0, 10, 20, 30, 40, 50, 60, 70. We can access and modify the elements using high, low, even, odd, these methods to indexing the elements. For example, we have a short dot high. We're going to assign the higher half of the elements to this new vector A. Higher half, because we have 8 elements, so for higher half, we're really looking at this 4, 5, 6, 7, these upper 4 elements. So we will assign this new vector to this vector A. In contrast, this short dot low will help us to get the lower half of this vector, 0, 10, 20, 30, and assign this vector to this new vector B. For even, they were referring to the elements whose indices are even numbers. So this will be 0, index 0 is index 2, index 4, index 6. So we're retrieving these 4 elements from this original vector. So this value 0, 20, 40, 60 will be assigned to this new vector C. Likewise, we can use these odd, high, even, this method to index a subset of elements in this vector and update with new values. Now let's combine what we have learned so far and look at a new example. Here we want to look at endianness, how the vectors are stored in a particular memory space based on the endianness of this OpenCL device. We have here an unsigned integer vector, and we have 4 elements in this vector. We initialize this vector in this way. The first element is a 32-bit integer, unsigned, and this is its hexadecimal value, 00010203. And the next one is 04, 05, 06, 07. And the third element is 08, 09, 08, 0B. And the fourth element in this vector is 0C, 0D, 0E, 0F. If we store this vector in a little endian device, and this is what we're going to see in the memory of this little endian device. First of all, we have 4 integers. So we'll have 4 integers, 4 unsigned integers, taking 16 bytes. This vector will take total 16 bytes. And each of this element will take 4 bytes. So in the memory space, we're going to be seeing these 16 bytes are used to store this 4-element vector of unsigned integer type. The first 4 bytes are used to store the first element of this vector. So this 0001, 02, 03 will be stored in the first 4 bytes. But because we use little endian, that means the least significant byte of this integer, which is 003, will be stored in the lowest address. And then the second to the least significant byte will be stored to the next byte. And then this 01 will be stored here, and this 00, which is the most significant byte of that integer, will be stored at the highest address for this integer. Again, the first 4 bytes are used to store the first element. And the next 4 bytes will be used to store the second element of this vector. So we're looking at this number here. This number is an unsigned integer. It has 4 bytes, and 07 is the least significant byte. This 07 will be stored at the lowest address among these 4 bytes because we're using little endian. And then 06, 05, and 04. And then we're going to be looking at the third element, which will again take 4 bytes. So these 4 bytes are used to store the third element, which is 08, 09, 08, 0b. 0b is the least significant byte for this integer. So 0b, this byte will be stored at the lowest address. And then 08, 09, 08, which is the most significant byte for this integer. And finally, we use the last 4 bytes to store the last integer element. And 0f is the most significant byte of this integer, and 0c is the most significant byte for this integer. So this is how we store 4-element vector of unsigned integer type on a little endian device. If we store the same vector on a big endian device, we're going to see slightly different memory layout. We will still use 16 bytes to store these 4 integers. The first 4 bytes will be used to store the first integer, but this time, when we look at this integer, the least significant byte of this integer is 03. Because in this case, we use big endian device, the least significant byte of an integer will be stored at the highest address. And in contrast, the most significant byte of an integer will be stored at the lowest address on a big endian device. So you can see that we store the integers differently in the sense that for the same integer, if it is a little endian device, the least significant byte will be at the lowest address, whereas if it is a big endian device, the least significant byte of an integer will be stored at the highest address. So among these 4 bytes, this location here has the highest address. And the rest of the integers follow the same rule, and you can see that they are slightly different from how we store the same integer on a little endian device. Now, next few lines, we want to show you a kernel function, and this kernel function is called vector bytes. It takes a pointer to a global memory object, and we are going to assign this vector, which is a 4-element vector of unsigned integer type, and we use the same initial values to initialize this vector. And then we will use this unsigned character pointer to point to this location in global memory. Here we declare a pointer p points to the beginning location of this vector that we just initialized. So you can think about p is pointing to the beginning of this 16-byte buffer. And of course, on little endian and on big endian device, the actual contents of these 16-byte buffer will be different. And then we're going to be initializing this test, which is the buffer in the global memory. We will initialize with the values at these pointers p, p plus 1, p plus 2, p plus 3, until p plus 15. What we're doing here is that we're going to be retrieving the individual bytes. This is how we're retrieving the individual bytes. We will increment the pointers by 1 at a time, and retrieving these values one by one. And then we use these values as the initial values to initialize this test buffer object in a global memory. If we do that, on the little endian device, the output of the vector bytes application will be in this order. So the test, eventually the test object in the global memory will have 03, 02, 01, 00, and then 07, 06, 05, 04, and so on. If this kernel function is executed on a big endian device, and the final result in the global memory object test will have a sequence of bytes like this: 00, 01, 02, 03, 04, 05, 06, 07, and so on. Memory alignment. Memory typically aligns on 32-bit structures, such as integers and floating point. They are always stored at memory address that is a multiple of 4, such as F0, F4, F8, etc. So you can assume that 32-bit structures are always aligned on 4-byte boundaries. 64-bit structures, such as long and double, they are stored at addresses that are multiple of 8. When the data structure is stored, in general, its memory alignment is set to the smallest power of 2 that is greater than or equal to the data size. For example, if you have a float 3, which means that you have 3 elements in this vector. Each element of this vector is a floating point, which takes 4 bytes. So a float 3 contains 12 bytes. If we store this vector, and it will be stored on a 16-byte boundary, because that is the smallest power of 2 greater than 12. You can control the data alignment, use align attribute, which can only be used when the data is declared. So you can, for example, declare a short integer x, and you want integer to be aligned to addresses of multiple of 4. We discussed how we use set kernel arg to initialize local arguments. You can configure arguments in the device local and private space by using set kernel arg. The last parameter value identifies the data that will be sent to the device as a kernel argument. However, you can't set the kernel arguments when the specifier is to local. Otherwise, you will receive a runtime error saying that's invalid argument value. The only time that we want to use local qualifier in a set kernel arg is to really tell the device to allocate local memory for a kernel argument. And in that case, you have to set the last argument of set kernel arg to be null. So you have something like kernel processing data, local floating point numbers, and once it's passed in from the host program, the kernel function will know that it will allocate a space in its local memory to accommodate these floating point or other data types. For private kernel arguments, you can initialize using a host application. In this case, the host needs to make the last argument a pointer to a primitive data. For example, it could be a pointer to an integer number, pointer to a floating point number, and so on. You cannot reference a private kernel argument. They must be simple primitives like integer and floating point. For example, you can have variable, an integer variable, number of iterations. You can assign 4 to this variable. You can pass in this value 4 using set kernel argument with the first argument, this is the index, and then size of this argument, which is the integer, and then you use the pointer to this variable number iterations, which currently has value 4. Then your kernel function, you should have something like this. Kernel function name, the first argument should be this one because you set this integer, this index as 0. And then in this case, this number iterations will be the private variable that you can use in your kernel function. Private kernel arguments can also be vectors. For example, you can have an array of 4 that's declared in the host program. By the way, float 4 cannot be used in the host application because float 4 is specific to OpenCL program. That means it can only be used in the kernel functions. So in order to pass in this array of 4, you can say set kernel argument, the index, then size of this array, and then the array, which implies the pointer to these 4 elements.